Hi there, I'm Adam. Here, I will describe how I approach designing proteins that exhibit facilitated dissociation. This is a useful behavior to design because in normal competitive binding, in which a target protein starts bound to a host protein, one first has to wait for the target protein to dissociate before a competitor protein can bind in its place. When the target binds with high affinity, this initial dissociation step is slow, limiting the overall rate of competition. In a facilitated dissociation process, this slow step can be bypassed. The competitor can directly bind to the target host complex and accelerate target dissociation. In this tutorial, I'll show you how I approach engineering arbitrary protein interactions to be rapidly dissociated, induced by an effector. This tutorial is a companion to a paper we just published. A link there is in the description. I'll start by describing how facilitated dissociation could work in proteins and the general approach we take to designing it. We start with a binder-target interaction. This can in principle be any or almost any protein-protein interaction you want to re-engineer. We also start with a switch protein that we designed to be ideal for this purpose. When this effector molecule is added, the switch is very strongly driven to change conformation. Switching back and forth between these conformational states, you can see the change the effector induces. We will use this conformational change to force the dissociation of the target from the binder. To do so, we will fuse the switch to the binder to make a protein which, in one conformation, the effector unbound state, binds the target normally, but in the effector bound conformation, strongly clashes with the target. Let's zoom in on that a little bit. You can see there's quite a large overlap between the switch here and the target. This clash causes the entire protein to deform into a strained high energy state, like this, which resolves the clash, but switching back and forth between this strained state and the clashing state, you can see that the entire protein is bending. And then from this strained state, the target dissociates quickly, resolving the strain. Now I'll describe how I approach designing this fusion. So the goal here is to fuse this switch to this binder such that one conformation of the switch allows target binding and the other clashes strongly with the target. So here I have my binder-target interaction in one object in this Pimal session. I have one conformation of my switch here and the other conformation here with the effector bound. Let's color this conformation differently so that we can clearly see the change in volume occupied by protein in the two conformations. And now let's explore some relative positions of these two components. So first I'll put protein in editing mode here. And in editing mode, you can hold down Shift and click with the left click to rotate the protein, or middle click to drag the protein around. So we can explore a possible fusion orientation of these proteins by rotating and dragging. And what I'm looking for here is to position the binder here relative to the switch such that I make nice contacts in a way that you could imagine building a fusion to, while also getting a clash with the blue switch corresponding to the effector bound conformation, but not the green, which corresponds to the effector unbound conformation where we want the target to be able to bind stably. So let's see, I still need to refine this a little bit. We don't have quite a strong enough clash here. And also this fusion looks a little bit funky. One thing that I normally do when I'm trying to envision what this fusion looks like is, because we're going to need to build a little bit more structure to actually make this a nice fusion, is I also drag around and place some placeholder helices, which will then in a way sketch what the fusion looks like. And then later we'll go on to refine that sketch into an actually plausible protein backbone. So one way that we can do this is we can just grab some random helices out from the protein. So if we go just in here, we can select this helix. And copy to a new object. And if we go back to this orientation, we can drag it elsewhere. And now we can kind of use this to envision what our fusion could look like. So in this case, our fusion would look something like, starting from the N terminus, we go to the C terminus here, loop over to this helix, and then from this end of the helix, loop to the N terminus of the binder. So that looks okay, but it's definitely still not great. I'm noticing the backbones look a little close here. And I don't think we got the clash right either. Yes, we still have some work to do. So let's pull this down a little bit. We need a little bit more space here to here for this helix to sit. So I'm thinking we could rotate this whole thing down a little bit and over. There we go. And something like that is looking pretty good. So what I'm looking for here, the most important thing is we want to make this fusion here between the switch and the binder rigid, so that the weakest part of the entire protein is the binder target interface. If the fusion here is weak mechanically, then it will preferentially bend instead of strain localizing to the binder target interface. And so you won't actually get that much dissociation. Let me give you an example of what that would look like. If we were to bend this over, maybe not that far, and we could put this helix here, for example. So this could still technically make a fully connected protein. You could loop from here to here, and then after this helix, loop from here to here, but you'd have this really extended structure, which would be mechanically pretty weak. This could just bend a little bit, and then the clash would resolve without putting very much strain on the binder-target interaction here. So it's really important that you make a rigid connection between your binder and your switch. So let's go back to the structure that we had, or approximately. Something like that. That looks all right to me. Let's do a bit more refinement here. I'm going to show lines. This is going to be a bit of a mess, but one other thing that I look for when I'm designing these fusions, particularly, so here if I hide the fusion helix, the original proteins that I'm fusing, the binder and the switch, are contacting here to here and a little bit also here to here between these two helices. So when we design these fusions, we'll generally keep the known protein components that we're fusing together fixed in backbone, and only redesign these kind of sketch secondary structure elements that we're including to visualize what the fusion could look like. So if we're going to keep these positions fixed here, we should make sure that the side chains are packing nicely between the switch side and the binder side. So let's zoom in on this. And the goal here is for these side chains along this helix and along this helix to be kind of interdigitating in the interface. If the structure was something like this, maybe that's not such a good example. Well, for a really drastic example, if it was like this, now you can see that this glutamine here and this alanine are kind of trying to occupy the same space, and that's undesirable. It's going to be hard to design like a good sequence stabilizing the fusion between these two, because a lot of the side chains are going to be trying to occupy the same space, and then there will be voids in between the helices. So it's better to slide things down a little bit, kind of like this, and space things out, so that here now you see like this aspartate here is occupying the space between these two alanines on this helix. This is also going to be refined later on in the design pipeline, but best to get it as good as you can manually first. And of course, just as a side note, this aspartate will not be the final residue in the final design. Of course, you won't put a charged residue like that in the core. So mainly just look at C beta position when determining this interdigitation. One other thing that I want to mention here is when using this switch, these two helices are less important. So if needed for the specific fusion geometry that you're looking for, you can actually get rid of them and rebuild them or something similar during the diffusion process. So if we want to look at that, can get rid of those. Then we can copy this helix twice. So we have 3 copies in total. Let's move one here. Flip this one over so that we get the correct looping order. And then finally we have that one. And now this gives us a little bit more flexibility to play with different positions of the binder target pair relative to the switch. Let's hide the side chains again. The final thing that I want to talk about is what this clash should look like. So let's kind of explore some different options here. One would be you could make the clash look something, quite drastic like this. And let's maybe play around with the fusion over here, these fusion helices, to see if we can find a nice looking fusion structure that could support this. Something like I think something like that looks reasonable enough. And of course, this will be refined later on. So these backbones aren't like binding. As long as it looks plausible diffusion can probably find a good solution. Okay, so now if we look at this clash here, a good heuristic for how the protein will deform is it will take the shortest path to resolve the clash. So in this case, probably the protein will deform by bending, like, um, the pink target here will move outwards a little bit like this, maybe bend around this sheet, and the switch will kind of bend outward this way. What we found is that, at least for this specific binder target interface, this is not a very destabilizing deformation. And so this kind of deformation doesn't actually accelerate dissociation very significantly. The best we ever got with a deformation that looked like this was maybe 100-fold, 120-fold. And the reason probably for this is, at least we hypothesize, is that beta strands and more generally secondary structure elements are more sensitive to deformations where you're shearing them, which would be deforming, kind of pushing down this way, compared to bending, which would be deforming kind of around in this direction. So this will probably depend on the specific binder target interaction you're trying to design facilitated dissociation into, but something to look out for could be the direction that you're trying to make things deform in. So I would vote that you sample a whole lot of different positions to try to sample a bunch of deformation directions, and then you can try to find the direction that works best for your particular complex. But in this case, what worked better was actually making deformations or clashes that looked more like this, which is where it looked a bit more like this. Let's see if we can again make this fusion nice. I think something like that could result in a good looking and rigid fusion. And so now the shortest path could be deforming outwards, but also it's kind of equally plausible that the proteins could deform downwards instead. So pink goes down, blue goes up. And this, for this particular binder target interaction, seemed to be much more destabilizing. We would get dissociation rate accelerations in like the thousands fold. Okay, so now I'll go load in a whole bunch of different positions that I've showed to show you how you might sample this, this space. Okay, so here are some examples of initial placements that I've made between the switch and this binder target pair. If I cycle through these, you can see how I'm sampling a whole bunch of relative positions of the binder and target relative to the switch. So this is kind of what you should do to explore the space of possible fusions and deformation directions. And if I load all of them in, yeah, you can see they're kind of spanning this variety of directions. So now what you would do is, starting from this state with the binder target and the switch in the non-clashing conformation without the effector, you would use, I would generally use fold condition diffusion to rebuild these three helices into like an actually good, plausible fusion structure. And I want to note again, this structure that we've built here that I'm sketching, this should be quite rigid. So a good heuristic is that each helix is contacting at least three others. which is true in this case. And if you're doing something with beta sheets, maybe more generally, each secondary structure element is contacting at least three others. So when you go to build these with diffusion, you would want to select residues on the interfaces of the components that you're trying to fuse together with the fusion region that you're trying to build to be redesigned. And you want to select these pretty carefully because you don't want to select residues to be redesigned that are involved in the function of the parts that you're trying to select. So, for example, residues like this residue or this residue are likely going to be involved in effector binding, whereas something like this residue will likely be involved in target binding. So I can show you how I would generally select these. If we show the lines again, maybe we can hide them for the fusion helices. I'm going to select every residue on the binder and on the switch interacting with these placeholder sketch helices that I think is also not important for the function of the switch or the binder. So I would say on the switch side, we can select these residues. I think that looks good. You can look at the direction of the C alpha C beta bond to see whether a side chain will kind of be pointing towards the fusion region. So like this alanine, for example, is pointing kind of back into the core here, so it seems less important. So we can color those. And those are the ones that I would, maybe this one too. Those are the residues that I would allow to change during the diffusion and later sequence design process. Now we can do the same thing on the binder here. So there's a difficult decision to be made regarding this glutamate here. Let's color the others and get rid of the selection so it's easier to see. So one could imagine that this glutamate could make a salt bridge with this, or maybe not a salt bridge, but at least have some sort of electrostatic attraction to this arginine here on the target, which may, so breaking that may reduce the affinity. But looking at this more, I think it's actually probably too far away, and this glutamate is more important for interacting with the arginine here. So I would not be worried about changing this. But you should use your judgment about changing residues close to interfaces. Okay, so the next step here would be to use this as an input to fold conditioned scaffold guided diffusion is generally what I would do. What you want to do is scaffold the switch, binder, and target as you've positioned them using the motif scaffolding function, so those remain fixed throughout the diffusion process, and allow these three helices to change, plus some region of loop that connects them. And generally what I would do is provide a matrix describing the adjacencies of the secondary structure elements in order to guide diffusion to build structures that look like what you've sketched. Scripts for doing this are in the linked code, and I've also linked the README for how this fold conditioned diffusion works in the description. All right, so here I'm showing one of my ultimate inputs to diffusion. In this case, I have done a little bit more position sampling between the switch and the binder and target using Rosetta Fast Design, which is why these helices look a little bit wonky. This is an optional step. Code for that is also included in the GitHub that I linked in the description. Anyway, so this is my ultimate input to diffusion. When we actually look at the diffuse structures, you can see that now, compared to the original structure, where these three helices are unconnected and just kind of placed in approximately where they should go in the final fusion, after diffusion, we have built a fully connected protein now. So from the N terminus of the switch to the C terminus of the binder, we have a fully looped protein. And if we look through all of these, you can see that diffusion is sampling the space of possible fusions that you could build kind of within this constraint of this topology that I've specified here, which is three helices kind of in this in these relative positions. And if we show the side chains, you can see that the side chains for the switch and the binder, so most of the sequence for those proteins remains intact, which is as desired because these proteins have already been validated. We don't want to change them too much. But in the new diffusion diffused region, these three helices, and also in the interactions of this new diffused region with the components we're fusing, you can see that also the sequence has been masked and needs to be redesigned. So on the backside of this helix, this helix here, and this helix here, the sequence has been redesigned. So then the next step will be to take these diffuse structures and use protein MPNN to design sequences for these regions which don't currently have a sequence. So here I have a structure just out of diffusion where the sequence of the fusion region has not yet been designed, nor has the sequence of the interfaces between the components to be fused with the fusion region. Now, if we switch to a sequence design version, you can see that MPNN has chosen residues at each position in this fusion region, and also at the interface with the fusion region on the binder and on the switch. So now I would generate, this is one example, but I would generate many sequences, and the next step will be to use AlphaFold to predict the structure of this protein. If the AlphaFold prediction agrees with the design model that MPNN designed, then that is likely a good design, and we can proceed with further filtering. So now finally, I want to describe how I filter designs. So this is a prediction of the MPNN design sequence for a generated structure. This, in this case, agreed very well with the design model that we fed into AlphaFold. Therefore, we selected this design for further filtering. So how do we further filter? Mainly, I use all model weight sets of AlphaFold to predict the structure of this protein in all possible complex states. So I have the 5 models, which all agree very well, of the apostate, 5 models of the effector bound state, well, in this case, 4 models of the target bound state, because the 5th model doesn't predict this binder target interaction correctly for some reason. And then again, 4 models of the ternary complex state. And we'll talk more about this ternary complex state in a minute. So the most important thing first is that AlphaFold predicts the state with high confidence, meaning a high PLDDT and low average PLDDT, as well as a high PTM, and that all 5 models agree with each other. So here, all 5 models, the RMSD among them is quite low. Same for the effector bound state. And we really robustly see this conformational change. All 5 models predict it with the effector bound properly. Again, very good agreement in the target binding states. And now let's talk about the ternary complex. So first, if we just were to load in these 2 structures, you can see that we have this designed clash here, which is of course non-physical. And so when both the target and the effector are present, the entire protein complex should strain and bend and deform to resolve that clash. And AlphaFold seems to do a pretty good job predicting, or at least suggesting some possibilities for what that strain state could look like. So here's one, and this is showing the kind of deformation that I mentioned earlier that in this case was desirable. So compared to the position of the target here, the unstrained position, you can see the target is deforming downwards, and compared to the ideal position of the switch, you can see it's deforming upwards like this, in a way that's putting shear on the secondary structure elements. If we cycle through the ternary complex predictions, you can see that AlphaFold actually, it varies a fair bit. So AlphaFold is less sure about how to position these things, or maybe it's a dynamic complex. But the main thing that you look for, I would say at least when ordering your first designs, is that AlphaFold is predicting the set of designs that you test to deform in a variety of directions with a variety of magnitudes. And you can pick out the deformation directions that work best experimentally and refine them by sampling more finely around those directions. Well, thank you for watching this tutorial. I hope it was helpful in describing how one could approach redesigning a binder to undergo facilitated dissociation in response to an effector. If you have any questions or have ideas which could benefit from dissociation, please don't hesitate to reach out.